Good afternoon, everyone. Welcome to the NIHHIS webinar series, starting with exploring the heat hazard. I hope you're all in the right place. Hope you're having a great day, and I hope you're ready for a really exciting hour with us. Thank you so much for making time in your day to show up. Couple of housekeeping issues. We have a question. We'll have questions and answers. So if you have questions, you can put them in the question box. And we have an exciting panel of 3 speakers, which you can see here. They'll be introduced in just a minute, but I'm going to start with just, again, a welcome and a thank you for being here. My name is Julie Turton. I'm with the National Oceanic and Atmospheric Administration. I'm in the Climate Program Office, and I officially lead the National Integrated Heat Health Information System, along with our colleagues in the Centers for Disease Control and several other agencies who are partners in this effort. I also coordinate NOAA's health activities and have been doing that for quite a while. So I'm really thrilled that you all are here, and we are, next slide please. We're starting this workshop series in the context of NIHHIS, which is the National Integrated Heat Health Information System. It's a federal initiative basically to coordinate the federal enterprise on extreme heat, but really to coordinate and provide information for people managing heat risk on the ground, which is hopefully most of you. We probably have some federal partners on the call as well. So NIHHIS is led out of the Climate Program Office and out of NOAA, like I said, with CDC as our core founding partner and several other agencies involved. Next slide, please. And we started NIHHIS to really figure out how to bring together the many assets, the great research, the great capacity that we had, not just in the federal government, but across the nation to manage heat. But to do so knowing that heat is on the rise, heat's expected to increase, extreme heat events are expected to increase, and we needed a better way of managing and understanding and dealing with heat risk on multiple time scales. So whether you're trying to do a better job of communicating about a heat wave, an imminent heat wave, which we've had way too much experience with recently, whether you're trying to manage the seasonal risk on, gee, should I open my cooling centers earlier? Do I need to have more staff on hand? Do I need to have more money in my budget to pay for cooling centers or for electricity bill supplements? Or do I need to be planning my cities differently or buying different building materials? A whole gamut of how we manage heat risk. NIHHIS was designed to pull those pieces together across the federal government and also to provide a focal point and engagement with those of you on the ground in cities and states and communities and companies around the United States and around the world, actually, that are trying to manage heat risk over the time scale. Next slide, please. So I just want to give you one slide about what we're doing and why we are so excited to launch this webinar series. NIHHIS has several, I already mentioned goals and some interagency partners. And actually, excitingly for us, several senators actually introduced a bill recently that would address heat. And so I think if you're interested in that, you should probably figure out what Senator Markey's up to and some of his colleagues. They introduced a bill yesterday that among other things will help address heat risk and establish formalized NIHHIS, so that was exciting. But I think the whole point of putting this slide up is not to go down a programmatic list, but that at the bottom one there, we're really talking about public-private partnerships, and we're also talking about a series of things that comprise NIHHIS. There's an interagency group, of course, that's a federal thing, but we really are looking for engagement and input from non-federal partners. There are a series of pilots, and you can see partners in research and communications and international are there, but I'm going to stop with pilots because what we're talking about today in this urban heat context is the main focus, and not the main focus of NIHHIS, but it's the main focus of the pilot right now is urban heat. And so you'll hear in just a minute some of the work we've been doing for several years on urban heat islands. And this webinar series is designed to bring together those of you trying to manage urban heat, understand heat risk, and address it in whatever time scale, to bring you together to learn from each other, and also so we can learn from you about what's needed next, both in research and operational context. So I'm going to turn it over to Nora Randall, who, next slide please, is going to talk a little bit more about the urban heat island campaigns. They have been a main focus of our NIHHIS pilot activities over the last several years. We've done other pilots that have been focused on other things, and we've done a lot of work on occupational health as well. So, and I want you to think this is the only thing, but this is certainly a really important topic. So Nora, thank you for organizing this. There's a whole team of people behind this webinar series. This is the first one, so congratulations to you and the team for launching it and getting it going. And thanks to our speakers, because I know they're all going to be fantastic. And please take it away and explain a little bit more about the UHI campaigns.
Hello, my name is Nora Randall. I'm a Canals Fellow for 2021 working at NOAA's Climate Program Office. And one of the areas that I'm working in is with the Urban Heat Island mapping group. And so one of the pieces that NIHHIS has been working on has been this Urban Heat Island mapping campaign that they have done in collaboration with Kappa Strategies and Heat Watch. And in blue, you see all the previous campaigns. We started this in 2017. And in black, you can see all of the campaigns that are going on this season and this year. And moving forward from mapping, we decided to move on and try and further utilize the information and energy from these campaigns. Next slide, please. So this is the extreme heat risk team, of which I'm a part of. We have Monica, Julie, Shay, who is also another Canals Fellow with me, Hunter, and Morgan, who is newly onboarded to this team, Sylvia Reeves, Tom DiLiberto, and Lisa Vaughn. And we're all in the Climate Program Office. And if you continue on, so we've created this this webinar series to further capitalize on what we've done with our Heat Island campaigns. And following this U.S. Climate Resilience Toolkit Steps to Resilience, we are looking first at exploring the heat hazard and then assessing the vulnerability and risk by looking at some of the examples of heat vulnerability indices that some of the campaign cities. And that webinar is scheduled for next month, August 17th, so stay tuned. And then we've broken up the next piece, investigate options, into 3 separate webinars. So the dates for those have yet to be established. Please keep checking back on our website for updates for when these webinars will come through. And the last webinar theme that we have right now is prioritize and plan. So there are a total of 7 webinars, and this is the first. And to start us off, next slide, please. Our first speaker today is Jen Runkle, Dr. Jen Runkle. She will be speaking today on the individual monitoring of temperature, exposure, and at work, a sensor-based approach. She is a trained environmental epidemiologist who serves as a research scientist at NC State's North Carolina Institute for Climate Studies and the Cooperative Institute for Satellite Earth System Studies within the academic arm of NOAA's National Centers for Environmental Information. Her research is focused on using causal science to rapidly understand how, when, and where local interventions may best be leveraged to reduce climate health inequities in underserved communities. So take it away.
Thanks so much, Nora. Good afternoon, all. Just as Nora mentioned, I'm going to talk about some research that I conducted a few years ago. And before I dive in, I want to give props to my team. This was most certainly an interdisciplinary effort. I worked very closely with my colleague, Dr. Maggie Sugg, a medical geographer at App State, Dr. Chris Furman, a meteorologist at Mississippi State, and Scott Stevens, our data guru, data wrangler at my institute here at NC State. So in the next few minutes, I just want to provide you a really high-level overview of exploring the use of wearable tech to capture personal exposure to heat in the workplace. Next slide. So across the US, temperatures have increased anywhere from 1 to 2 degrees Fahrenheit since record keeping began. And we're expecting to see even higher temperatures with an increase somewhere between 2 to 3 degrees by mid-century and 2 to 4 degrees by late century. Recent and projected changes in temperature extremes, including the intensification of heat waves, present a persistent health threat for urban residents. And while we've observed population tolerance to these extreme heat events over time, due to increases in use of air conditioning, physiologic acclimatization, we all know and understand that there are limits to our adaptive capacity. Next slide. A warming climate is expected to result in days that are warmer than today's usual temperature and lead to increases in premature heat-related deaths. And studies primarily conducted in urban areas have revealed that extreme heat is connected to excess emergency department and hospital visits for a number of chronic conditions, including diabetes, cardiovascular disease, mental health, and even pregnancy and infant health. And we also understand on the public health side that certain medications prescribed to address these chronic conditions can increase sensitivity to heat stress. And this is by no means an exhaustive list. Next slide. So past heat health research has really relied heavily on coarse weather station data, but we know that extreme heat measurements have really largely been crude in terms of spatial and temporal resolution, with high potential in underrepresenting true individual exposure for populations. This is a map of weather station networks across North Carolina, and you can see quite easily that these networks are not equally distributed. So there have been significant improvements in our ability to conduct granular measurement of temperature exposure with recent advances in sensor technology that provides a really low cost and easy way to collect real-time measurement at the individual level. And so what's really neat about this technology is it not only allows us to supplement coarser weather station data, but it also provides us on the science side a really unique way to engage non-traditional citizen scientists or even underrepresented groups around the issue of extreme heat. Next slide. So adverse health impacts of exposure to hot temperatures really do vary geographically and across vulnerable segments of the population, making it really difficult to apply universal temperature health thresholds across a range of urban environments. We know that variations in heat exposure exist due to individual level differences in mobility patterns and microenvironments. And outdoor workers are one particular group that is at risk of the health consequences of extreme heat. But in addition to health consequences, we're seeing a really important change in labor capacity. So a headline finding from the 2020 Lancet Countdown report showed that rising temperatures were responsible for an excess of 300 billion potential work hours lost globally in 2019. And this is a dramatic increase from what was observed in 2000. And we know that there's a large proportion of the work sector here in the US that's comprised of outdoor workers or workers who work in physically taxing and hot indoor conditions, including construction, parks and recreation, armed forces, and agriculture. Next slide. So population health experts have really traditionally relied on collecting survey data and taking personal observations, or even relying on time activity diaries to reconstruct temperature exposure histories. But we know that these methodologies are subject to recall bias and may result in a dilution or underestimation of the true experience of temperature exposure. And so new and emerging work has begun to explore the use of wearable technology to characterize personal exposure to heat. There's been a number of studies conducted to date. This is just really a short list, but where my research team comes in is we wanted to take the science a little bit further and pair environmental data, so temperature data paired with geolocated changes in physiologic heat stress, to help individuals make the connection that their real-time changes in temperature exposure are resulting in real-time changes in physiologic heat strain. So next slide. So we know that these outdoor workers are particularly vulnerable to the effects of climate change in a warming world. And not only are these kinds of exposures related to heat-related illness as well as stress and fatigue, but workers are at risk for increased risk for injury and even declines in productivity, which we just saw by the Lancet. So we set out to test the feasibility of using personal monitoring to characterize what individual temperature exposure looks like in outdoor workers. And we had three primary aims. We wanted to see how well sensor data compares with weather station data. What were those individual personal, occupational, and even behavioral factors that influenced physiologic heat strain? And could we use these data to get exposure health response relationships between temperature and heat stress? Next slide. So we really had three phases of work. The first phase was really formative research, just working closely with workers to determine how open they were to wearing this technology and allowing us to geolocate their work day, how they move throughout the work day. And the second phase was actually equipping workers with iButtons and a Garmin Vivo Active Watch to collect these temperature and health endpoints. And then the last phase was largely around how do we actually give these data back and report back the results of these studies in a way that workers can understand their individual exposure and actually move understanding into taking action. So each of the investigators approached our outdoor grounds management workers and across 3 universities, and we really each of the universities represented kind of a distinct climatological work group. For example, our App State University group of workers were characterized as the moderate heat exposure group. North Carolina State was our high heat work group, and then Mississippi State was our high heat plus high humidity work group. We've published a number of studies, but I'll give you just kind of a sneak peek of what we found. Next slide. So we worked very closely with grounds management workers and managers to recruit workers across the 3 universities to participate in 5 days of data collection. We collected a lot of endpoints, including baseline survey data concerning prior heat-related illness at work, their perception of heat as an occupational hazard, all the way to collecting temperature data using iButtons and Garmin heart rate and GPS coordinates, as well as wanting to kind of be able to track and corroborate what we were seeing with the wearable tech. We collected activity logs just to make sure that the temperatures we were seeing could be accounted for and the actual work that workers were engaging in for that work week. Next slide. We used these really low-cost, small iButtons to measure temperature. We also bought a few. We actually were able to obtain some pilot money from NIHHIS to buy temperature sensors, and had each work site, we worked really diligently to have iButtons that measured both temperature and humidity so we could pair in the humidity data. Next slide. We used the Garmin Vivo Active Watch to capture how the worker was moving throughout the workday, as well as heart rate and velocity and a few other health endpoints. Next slide. And so the first aim, how well did the individual experience temperature match with what we were seeing with the weather station data? And this is just kind of a snapshot. But essentially, we saw largely across the 3 work groups that weather station data was underestimating the workers' temperature experience, but the highest level of underestimation occurred in the morning time. Next slide. We were also able to map geographic hotspots across the campuses and pair that with spatial exertion data just to get a sense of where workers were experiencing the hottest temperatures and what time of the day. Next slide. The second aim was to look at what were those personal, occupational, and behavioral factors that influence physiologic response to heat strain. And so we looked at age, BMI, marital status, race and ethnicity, education, and even prior or comorbid medical conditions, as well as a number of workplace factors and even behavioral factors like did workers use personal protective equipment, did they take rest breaks, and even access shade when available. One point to note is we used a really basic level, our basic definition of heat strain, where we just subtracted a worker's sustained heart rate over 180 minus the individual's age, and heat stress, we just looked at maximum heart rate over 145. So next slide. And so what we found was a really interesting mismatch between the workers' perception of heat as a hazard versus their experience of heat. And in fact, our hottest, so our high heat plus humidity group, our highest exposed group was Mississippi State, and they really had a low perception of risk concerning heat in the workplace, but yet had the highest experience of heat stress. Next slide. We looked at a number of individual factors and kind of high-level results. We saw that workers who were older, who had experienced a prior heat symptom in the past week or in the past year, and who had high perception of heat as an occupational hazard had the lowest risk. Kind of on the contrary, we saw workers who had higher levels of education and a place to cool off were more experienced more heat strain events. And we kind of hypothesized that largely workers with higher education were in managerial positions and were likely not acclimated nor required to work in the heat kind of on a daily basis, but was more working outdoors at an intermittent level. Next slide. And so the last aim was just to look at the exposure response relationship between individual temperature experience and heat strain or heat stress. And we used a really flexible modeling approach, the distributive lag nonlinear model, to assess this relationship. Next slide. And so this is the results looking at relative risk of heat stress for both for all work groups combined. And we saw that the highest risk of heat stress really occurred anywhere from 85 to 95 degrees. So we were seeing that as workers were working in warmer temperatures, they were at higher risk for heat stress, as we would anticipate. Next slide. One really interesting finding, so during our research study, we had the National Weather Service issue at least 2 heat advisories, which the weeks that heat advisories were issued are circled in blue. And so what we found is that during those weeks, workers were actually modifying their work schedules and exhibited a lower risk of heat stress. And so we saw something interesting. We saw the highest risk of heat stress or heat strain occurring in these kind of seasonally above warmer than average temperatures, but not warm enough to elicit a heat advisory or heat warning. Next slide. And so what we found is that personal monitoring devices were a really feasible method for our group to characterize the personal experience of temperature for outdoor workers. We did note significant variability in heat stress response among similar occupational work groups. Workers were modifying their heat exposure during those weeks where warnings or advisories were issued, and spending more time indoors. We also conducted a cold study as just by request of workers, and so I won't go into that. But you know, heat waves are expected to increase in frequency and intensity, and the way that local residents respond to such incidents really depends on their understanding of heat risk, their way of life, the jobs that they work, their access to adaptive resources in the communities to which they belong. And wearable technology really is a promising avenue to empower underrepresented and urban communities to kind of go in and capture high resolution environmental monitoring data for temperature and physiologic or other health endpoints to better understand, how communities can engage and creatively address place-based heat health concerns and derive kind of adaptive or mitigative plans that are really locally specific. And in fact, our research group is part of a larger project this summer in the city of Charleston. We know the city of Charleston is really warm. It provides an excellent case study to look at local resilience efforts. And so the city was selected to be part of the NIHHIS and Kappa Strategies Urban Heat Island campaign. And so while that Urban Heat Island campaign is going on, we're going to be working to partner and capture personal monitoring, personal temperature experience in workers across the city, and pair that with other relevant measures like wet bulb globe temperature and sea breeze, just to kind of look and see what the data are telling us about ways that Charleston can be more resilient in the face of extreme heat. I will say the research is evolving, but on the air quality side, personal monitoring methods have been recently used, particularly in California, as in community-driven data monitoring to influence local and state public policy. And so we've got a long ways to go, but it may be an interesting way. Personal monitoring studies, or citizen science projects, may be an interesting way to not only engage vulnerable communities, but also kind of rally around local heat prevention strategies and potentially inform local policy. So with that, I will pass the baton to our next speaker. Oh, and I will say this was, we had such a great time working with our workers. They were fantastic, and a lot of thanks to each of the outdoor workers at each of our work sites, and ORAL and a few other places that we received funding for this work. Thank you.
I have two questions, but maybe Jen can answer that into the group message while I introduce Brian. One is, did you record the observed wet bulb globe temperature and or heat index during the study, and whether you have the results from the study published? I believe you're muted.
Oh yeah, so answer now or in the chat box?
Could you answer in the chat box, please?
And got it. Thank you so much.
Okay, our second speaker today is Brian Garcia. Brian has been a professional meteorologist for 16 years, beginning his career within the private sector before joining the federal government with the National Weather Service. Weather was not always forefront on Brian's mind, but did play a role in everything he did. Growing up in the Pacific Northwest, mountain and marine meteorology were critical to his recreation. From climbing to backcountry snowboarding to surfing and camping, everything revolved around weather. Once this connection was made, Brian was off into the world of weather. He is a graduate of the University of Washington and has followed positions in Houston, DC, Eureka, California, and now Monterey, California. In his current role as the warning coordination meteorologist for the National Weather Service's San Francisco Bay Area, Monterey Bay regions, he is tasked with building partnerships across a diverse sector of communities. Through this role, he translates technical weather information for partner agencies to take action on in order to protect lives and property. He also is allotted the opportunity to work with NOAA on projects such as the Urban Heat Island campaign. Outside of work, you'll typically find Brian in the waters of Santa Cruz surfing as much as possible. Okay, well, take it away.
Thanks, Nora. And let's see here. I'm going to go ahead and hopefully you can see my screen. I'm going to pretend that you can and just get ripping through this. So my name is Brian Garcia. As Nora said, I am the warning coordination meteorologist for the San Francisco Bay Area and Monterey Bay regions with the National Weather Service. It's a fantastic job because that means I get to go out and talk to people about actually what all of this, like what Dr. Ronco is talking about in terms of heat, what it means on the ground. So I'm going to rip through some slides and we're going to go over quite a few things. And I apologize to the organizers. I did update my slides after I sent them to you. So these are updated slides and I'll get them to you. But we're going to talk about observations, weather model integration, output forecast process, what we call heat risk out here in the West. And we'll talk a little bit about that. It's probably where we'll spend the core of the time here. And then talk about the Urban Heat Island campaign and what it looked like in our area, in the San Francisco Bay Area. And then we'll talk a little bit about community actions. So observations, first up, God, we love data. The more data, the better. So when we're talking about wearable things, it's like, this is fantastic because that's just more data, right? And so long as that data is calibrated, is good, and is essentially statistically significant, we can start to integrate that data into our observation network. And this is kind of a snapshot of the network of observations that we have. Everything from buoys out in the ocean to satellites up in space that look at cloud temperatures and ground temperatures and all that sort of stuff. This is just a snapshot of a lot of weather stations around the San Francisco Bay Area. This is the area that my office gets to serve. And we have a lot of weather stations around the area, but you can see once you go out into the Central Valley and then up into the Sierra Nevada mountains there, the observations get thinner. So it's always good to fill those in. And if we get to a time where we have wearable technology that gets that data and reports it back up, that's going to be great. Because ultimately what happens is we take all of that data and it goes through the, and I'm going to try to remember this acronym, Meteorological Assimilation Data Ingest System, if I have that right. So otherwise, NIHHIS. By the way, in NOAA, we love our acronyms. NOAA, you think, stands for the National Oceanic and Atmospheric Administration. It's actually the National Organization for the Advancement of Acronyms. So that's pretty much all we live off of here. But we take all this data and we shove it into that ingest interface, and we take NOAA data and we take non-NOAA providers as well, as you see where you see there in those globes, and it goes into the ingest, gets processed, database, and distributed out to the meteorological community. And you can see it kind of in a little box graph below there. So observations, analysis, forecast. And that's out there for everybody to use. So the private sector, like when you think, like Weather Channel or Weather Underground or other places like that, they're all using this data that we have from NOAA. So that data gets outputted into formats like this. And this is something you might see on the nightly news or something like that, but we get all these weather models. And so not only do we get weather models across like the horizontal plane, so we get to see from east to west, north to south, but we also get it in the vertical as well. So from the surface all the way up into pretty much up into space. So this, for example, is just precipitable water, how much water is in the atmospheric column that's potentially to rain out. But as meteorologists, then we sit in our little office chairs and we analyze all this data. And as we analyze this data, then we start to make a forecast out of this data. And when I started, we did a lot of this by hand. And granted, I've only been doing operational meteorology for like 16 years, I think it is, something like that. And it was really all done by hand. It was very hand driven. Now we have a lot of great tools thanks to some really smart people out there that have developed these tools for us to take all of this data, essentially post-process it, like really dig into the data automatically, and then give us the first best guess. And so we don't spend nearly as much time handcrafting forecasts like we used to. But still, if you remember when you were a kid and your mom or your father or whoever watched you was asking you to do paint by numbers, that's essentially what we do in the National Weather Service. So we have this process here where we literally go through and paint by numbers. And this is the temperature grids is what we call it. And each little pixel is 2.5 kilometers square. So we paint those grids in terms of the temperatures that we think are going to happen at that time based on all the observational data through the models and the output to us. And so then we take that data, we take that forecast, I should say, so we have high temperatures, we have low temperatures, we have maximum relative humidity, we have minimum relative humidity, and it all gets slammed together, and that's when we can really start looking at the impacts of heat. Now, in other parts of the country, you'll hear like global wet bulb temperature, you'll hear heat index. Out here in the West, people much smarter than I, you developed a thing called heat risk. And heat risk, what it looks at is the daytime high temperature forecast, and as well as the low temperature forecast, because ultimately we don't have a really strong, robust, long-term data set for humidity. And because of that, we can't have like a climatology for humidity going back as far as we have temperature. So using temperature, we can actually look at those minimum temperatures and draw out essentially what it's kind of a proxy for humidity, because if it's warmer overnight, you have a higher humidity overnight because it's holding that heat in a little bit longer. So this one, these charts are from Portland. I just want to describe these really quick because they are color coded, and the colors are very important to what we use in the West called heat risk. So down in the green, and I hope you can see my mouse, down in the green area, that is, we're good. We're not worried about anything. There's not much heat risk for anybody except for the extremely vulnerable populations, and even then, they're probably really not at risk. The yellow area, that's when we get into, okay, now the really vulnerable populations are starting to see an enhanced risk of heat exposure and heat threat, so that heat risk. Then you get up into the orange areas here, and that's when a broader segment of the population is susceptible to heat risk. So now we're not just talking about the vulnerable, but now we're talking about even healthy people that might be, as Jen was talking about, out there in the fields and working. So here in Monterey County and Santa Cruz County, we have large agricultural industry. So this is the time where people might take those precautionary measures to take more breaks, get shade, get more water, things like that. And then up in the red, that's where we are for that high heat risk area. So once we get up into the highest heat risk area, all segments of the population are susceptible to heat impacts. So heat stroke, heat exhaustion, things like that. And that's where we start to see the morbidity go up. And so you can see how the lines like nudge up during the summer months. This is all based on climatology. So think about it this way. In, let's say, March, April, May, maybe April, May, you know, you're just coming out of spring and winter, it's been kind of cool, and then all of a sudden you have this spike into the heat. Well, your body hasn't acclimated to that yet. So because your body hasn't acclimated to months of summer heat, you're going to have a higher stress on your body. So that higher stress on the body is reflected in this data, so that we are issuing a heat advisory or an excessive heat warning at a lower temperature than we might be later in the summer. So now you're thinking like late August when it's really hot, but you've already seen like a month and a half, 2 months, 3 months of heat, and your body is acclimated to that. So the heat stress might not be as profound during that time. So that's the reason you kind of see that nudge in that orange and red line following the temperature data. And by the way, those solid lines and then the dots, that's all temperature data. So, okay, let's move on. So social vulnerability index is also included into the heat risk. So all of those little 2.5 kilometer squares that we forecast for, those have a specific social vulnerability index associated with them. And that helps drive the heat risk as well. So places that might have, let's say urban areas where it's very hot during the day because of the urban heat island effect, or has a higher degree of highly vulnerable population, maybe the unsheltered population, you know, those are going to be areas where that heat risk might be higher because of the vulnerability index. So ultimately out west, this is what it looks like, and I took this screenshot yesterday, so this is for tomorrow. And you can see up in the Pacific Northwest, you see a lot of red out through there. So that's the time when we're looking at issuing heat advisories, potentially even excessive heat warnings. When you start to see some of the magenta, like in Eastern Oregon, or even little pockets in on the east slopes of the Cascades there in Washington, those magenta areas are excessive heat warning timeframes. So that's when we're coordinating with our partner agencies to make sure that they know this information and can act upon it. So you can see here just a quick snapshot, heat risk values, heat risk effects, and level of concern. So I'll just let you digest that for a hot second, and we're done with that. So with the heat products, we'll issue excessive heat warnings or heat advisory if it's not as high as that warning level. And for example, last year in August around here in the Bay Area, it was right before our lightning event, this is what we had out. So we had a lot of areas under excessive heat warning in California and a lot of areas under excessive heat advisory. And so these are the times, I'm going to skip those really quick. These are the times when community actions really come into play, and our partner agencies start to open cooling shelters for vulnerable populations, people who might not have air conditioning, people who might be unsheltered, places like that. And so now the Urban Heat Island campaign came into the San Jose area last year, San Jose, Santa Clara, and did this great mapping. They drove around the area and they took temperature measurements, and it was really fantastic because you can see up near the water by the bay, it's a little cooler, but you can also start to see pockets of hotter temperatures out in East San Jose. And then as you get down south into South San Jose, even down into the city of Morgan Hill down there, it gets warm even up in the mountains. And then Santa Clara University paired this with modeling data, and they kind of filled in those gaps with the models, and you can really start to pick out the pockets of heat. So this is a really important facet to planning for partner agencies for heat, because now you can start to identify areas that might be of higher risk than others, so you can move resources, distribute resources in certain ways when this data is available. So the Urban Heat Island campaign is really helping out. This summer we have it going on in San Francisco. And ultimately, this all kind of pairs together and bubbles together to make sure that we have a weather-ready nation so that people can respond to weather-dependent events and hopefully at the end of the day, save lives and save property, because we don't want people to die of heat. It's a completely preventable cause of death. So that's it for me. If you have any questions, I'm always happy to answer those, and I will stop sharing my screen.
Thank you, Ryan. If there are any questions, please type them into the question box. Give it a minute before I introduce Cameron.
Yeah, hopefully I kept under time.
Oh, you did. Great. Do you want to, can you tell some anecdotes? Oh, there's Cameron. Great.
Yeah, let's do that.
And then please feel free to type in questions. I can send them on to the panelists, and there'll be time for questions at the end as well. Okay, so we have Cameron Lee, Dr. Cameron Lee. He is a climate scientist with research interests mainly in applied climatology, focusing on utilizing synoptic methods in a variety of applications, especially human health, mortality, and coastal environments, often incorporating climate change. His current NOAA-funded research utilizes synoptic climatology to examine various human health-related multivariate indicators of climate change, while another NOAA-funded project uses circulation patterns to help predict daily scale sea level variability. Previous grant-based research includes projections of future heat waves and heat-related mortality in California due to climate change, and assessing the impacts of weather on asthma in New York State. Earlier research has included the development of a gridded air mass classification system, which is now updated annually, includes daily forecasts, and has been expanded to a global domain with nearly 260,000 locations. The system was transformed into 2 global scale indicators tracking our changing climate. In addition to Cameron's research activities, he has co-authored 5 review articles on the topic of synoptic climatology, reviewed grant proposals for the National Science Foundation, served as a peer reviewer for over a dozen academic journals, and presented research at dozens of national and international conferences. He is also serving as the managing editor of the International Journal of Biometeorology. Take it away.
All right, well, thank you. Hopefully you guys can all hear me. Big thanks for, or a big thanks to Nora for organizing all this, and thank you guys all for tuning into our talks here and sticking around for this one. Before I go too much further, I would like to acknowledge one of my colleagues on much of the research that I'm going to be going over here today, Scott Sheridan. You see his name up there on the screen. He just couldn't make it today. As my title suggests here, I'm going to be building on Brian and Jen's talks by expanding this kind of to a larger scale, right? Going from kind of the micro scale up to a regional and continental scale, and take that continental scale approach to how climate change is influencing the myriad metrics that impact human thermal comfort. Next slide, please. All right, so I'll start off talking about the term global warming. Global warming, right? I mean, we all have obviously heard of this term, but I've never really liked this term and prefer to use the term climate change. And it really is more than just semantics, as most people might argue. And it kind of provides some of the impetus behind this research that I'm going over here today. Global warming really isn't descriptive enough. It leaves out important parts of the changing climate, as I'll go through in my presentation. First is the fact that average temperatures, while obviously very important from a statistical sense, it's the most common statistic averages and means are that we use. Averages really aren't all that impactful, right? I'm sitting here in Kent, Ohio. I'm not being impacted by an average meteorological day, right? It's really the extremes that have much more of an impact, right? The extremes are much more impactful. Further, averages don't tell us anything really about variability. For example, let's say a city has an average temperature of 50 degrees Fahrenheit. Well, is that because it's 50 degrees Fahrenheit every single day? Or is it 100 degrees Fahrenheit on half the days and 0 degrees Fahrenheit on half the days? And therefore it's an average of 50, right? Now, obviously I'm exaggerating here. There's no place that has a climate that's that crazy, but you can see my point. There's two very different climates, one with a lot of variability, one with absolutely no variability, yet they still come through with an average of 50 degrees, right? And so what I'm saying here is that it's not only important to see how averages are changing, but it's also important to see how variability in temperatures and other metrics are changing through time as well. If that first city that I mentioned that's 50 degrees all the time is becoming much more variable, or that second city that I mentioned that's always 100 or 0 is becoming much less variable, that's something that, quite frankly, we need to take into consideration because it has important impacts in terms of extremes as well. The top graph shows, the one that's kind of animated here, shows summer temperatures in the Northern Hemisphere over 4 different periods. That one right there starts off with the 1951 through 1980 climate normal period. And you'll see that it kind of shifts through time here. Now, obviously, the big thing that everyone noticed is the overall distribution is moving to your right, okay? And this is, what we all think of as a changing average temperature. But in addition, a little bit less obvious, is the overall distribution is also kind of flattening out, right? It's really steep right there. And then as it goes through, it has a tendency to flatten out. What this means is that variability is increasing. The tails of this distribution are getting fatter, which means that extreme temperatures are becoming more frequent faster than the average trend alone might otherwise suggest. As a result of this, we are seeing, and will continue to see, kind of an onslaught of extreme and, quite frankly, unprecedented temperatures. The bottom graphic kind of gets at this a little bit, similar to one that Brian just showed earlier. This shows very well the unrivaled warmth in the city of Portland last month, just almost a month ago today, I guess. Every dot here is one day in terms of the maximum temperature for that day, 1979 through 2021. And the 3 red dots at the top are a few days at the end of June. I don't remember exactly what 3 days those are. You can see they are well in excess of any day in June, and 2 of them are well in excess of any day ever, with August usually being the hottest time of the year in Portland. In addition to statistical nuance, the term global warming also doesn't really capture the manifestations of climate change that kind of differ by location or by season. Nor is the term inclusive of the various different meteorological variables that we all know contribute to human thermal comfort, how comfortable people are with their environment. Next slide, please. So I'm going to be getting into that here over the coming slides as the last few bullet points. If you'll see on this slide, if you can get the animation going by pressing, there we go. Trends and averages aren't always reflective of expected changes in extreme events, as I suggested earlier with a moving graphic. For example, one of the places that's heating up fastest in the world is the Arctic, heating up about twice as fast as the global average. Therefore, you would expect in the Arctic that extreme heat events would also be increasing at a similar pace, greater than average, possibly even twice as fast, right? However, for some places like northern Canada in autumn, here you see the, you guys can't see my mouse, you see the big red circle that I have in that map in the lower left or lower right hand, thank you, lower right hand portion of the screen. The first graphic that has the red, white, and blue colors shows average trend in temperature. Reds mean it's getting warmer over time, blues mean it's getting colder over time. The second map that it fades into is trends in extreme heat events days. If you see a purple color, that means that heat event days are becoming more frequent. A green color means that heat event days are becoming less frequent. And what I want you to focus on, obviously, is that area where I have the big red circle. We see in autumn, the temperatures are drastically increasing, as we would expect with this idea of Arctic amplification, the Arctic warming twice as fast as the rest of the globe. However, when you look at extreme heat events, the heat waves, if you will, that trend disappears. You would expect heat events to go up with increasing temperatures, but that is not what we see. Part of the reason for this is we're seeing a significant decrease in temperature variability in the autumn, October, November, and December. And this is likely due to the delayed sea ice freeze up in this area, making the area more of a maritime climate in those months than it used to be when the sea ice was there, had a much more continental type of climate. We can see this reflected in the graphs that I have on the right-hand portion of the screen, especially the top right-hand portion graph. You'll notice with that graph, the gray line, represents how the climate used to be. The black line represents how the climate is over the last couple of decades. You'll notice that yes, the black line has moved rightward, meaning the average temperature has increased, but notice what has happened to the distribution, right? The peak has increased, the tails have thinned out, and what this has equated to is we're getting a lot less cold events, but no change really in heat events, as climate change is warming the environment there in northern Canada, especially for autumn. These oddities are also noted in other areas. The middle graph shows an oddity for the western US where cold events are actually increasing despite no real trend. The lower graph is for the southern plains in summer where there's very little change in average temperatures, but a significant increase in heat events due to a much more negative skew in the temperature distribution. The other thing that I want you to note on the maps that continuously change colors here are that the extremes and the averages too are not necessarily what I will call seasonally uniform. That is to say, these four maps are different from each other. Each map is showing a different season, right? And when you quote a statistic like the Arctic is warming up twice as fast, you might expect that that warming is going to be equal in all seasons. Well, it's not. It is concentrated mostly, as you can see here, in autumn and summer for both extreme temperature events and averages, while if you look in winter and spring, you don't see nearly the same trends. And so seasonal variability is something that's also very important. Next slide, please. The other thing I want to talk about here is relativity. Plenty of research has shown, especially when it comes to human thermal comfort, it's not one size fits all, right? High latitude locations, so locations nearer to the poles, often have a lower tolerance for warm temperatures than more tropical locations do that are used to the heat. Oppositely, tropical locations have a low tolerance for extreme cold, compared to populations that are used to it that are closer to the poles. So a 90-degree spring day in Florida isn't going to have the same impact as a 90-degree spring day in Minneapolis, where they just really aren't used to that kind of heat. The image on the right shows this difference for 3 different areas: North Carolina in the top graphic, England in the middle graphic, and Finland in the graphic at the bottom. Now, this isn't from my research. This is from some research. I have the citation in there. Donaldson et al., I believe, 2005, showing where thermal comfort is. In North Carolina, that gray bar is somewhere around about 25 degrees Celsius. In England, it's somewhere around about 20 degrees Celsius. And in South Finland, it's about 15 degrees Celsius. That's where mortality is at its least. And you can see with extremely cold temperatures, Finland doesn't have the same response as Southeast England does. With extremely warm temperatures, North Carolina has almost no response in terms of mortality, while England and southern Finland have quite a response, right? So basically, this is getting at with depending upon the type of climate that you are used to, you might have a different type of response in terms of, the amount of mortality you are getting in your location, or the amount of heat-related illnesses you're getting in your location as well. The other thing that I want to show is in the maps that I have on the left-hand portion of the screen. Similarly to relativity in terms of location, there's also relativity in terms of season. I described this a little bit in the previous graphic, but we explored this in some recent research where we have looked at extreme seasonal events, right? So think extremely warm winter days or very cool summer days. How are these things changing? What we did is we described relative extreme heat events and relative extreme cold events, which are depicted in the 2 maps at the bottom of the screen. These relative events grab fewer headlines, but they can have very important impacts on the environment, on agriculture, and on human health as well. As you can see in the image on the left, the patterns for relative events are quite different than those of the regular events, the 2 maps at the top of the screen. And for both heat and cold, the relative events are actually changing quite a bit more than the heat events, and they're changing in different places as well. The way we define these events also took into consideration the fact that persistent events, those events that last multiple days, can compound the effects of just an isolated event that might be separated by a day of cool weather. This is because people without access to air conditioning, especially in a heat event, if the overnight load doesn't get cool enough, their body never has a chance to recover. And therefore, 2 or 3 or more consecutive days of heat can be particularly problematic. And so we use a technique called the Nairn heat or excess heat factor in order to define these events that takes that persistence into consideration as well. Next slide, please. And then finally, I want to discuss air masses as a different technique to assess human thermal comfort and a different way of looking at climate change. As everyone in this room is probably well aware, there's a lot more than just temperature that impacts somebody's human thermal comfort, right? On a larger scale, it's more useful to model the synergistic impacts of all contributing meteorological variables, right? A person isn't exposed just to a single weather variable acting in isolation, but rather kind of the entire weather situation, and that can impact their thermal comfort. And so what we did is we looked at these multivariate weather or air masses, right? You can see these air masses defined in the graphic that I have on the right-hand portion of the screen, anywhere from dry and cold to hot and humid on one axis, or humid and cold to dry and warm on another axis. And on the map, or all the set of maps that you see in the left-hand portion of the screen, you can see the trends over time over a 40-year period. You'll note that we see different trends depending upon the different air masses. Obviously, all the cold air masses are decreasing, all the warm air masses are increasing, but it's not uniform, right? The humid and warm air mass, for example, is increasing quite a bit throughout most of Canada, but it's decreasing in the desert Southwest. Oppositely, the dry and warm air mass is increasing in the desert Southwest and decreasing in the Pacific Northwest, where humid warm has a tendency to increase, right? So if we just looked at temperature, we'd be missing these nuances of all the other variables that impact human thermal comfort. All right, and my last slide, please. All right. So obviously I'm kind of short on time here with Nora joining back in. My main goal was to kind of stress all of these nuances of climate change with regard to, you know, how they impact human thermal comfort. And I didn't even get into things such as mortality, displacement, changing demographics, physiological and behavioral acclimatization. All of these things are going to impact heat-related mortality as we move further on in the future. In order to make useful projections of the future, you really have to synthesize all of these different factors into actionable information. With that, I'll turn it back over to Nora. Thank you.
I'd like to thank our panelists, so Cameron Lee, Jen Runkle, and Brian Garcia, who took their time out to take time out of their day to present to you. And just a reminder, we will have further webinars. Please check back at our website for updates. The next one is going to be this on August 17th. The time is slightly different, so please keep checking back at that website. If there are any questions, or Julie, take it away.
Sorry, still muted. So thank you all. Thank you, Nora and team, for organizing it. Please do sign up for the next webinars, and you know, we'll keep you posted. We've got your emails and the like. So thank you all for showing up. And please let us know if we can do other things that will help you manage your urban heat risk. You know, we've got the webinar series kind of to connect us, but please be in touch. You've got the website, NIHHIS. If you just Google NIHHIS, you'll find us. And please be in touch. Let us know if you have questions, and we will post the webinar on the website in a, I don't know, a day or so. So, and Nora, team, thank you. Nora, Shay, Hunter's on the phone, but not here, was in transit today. Thank you all so much for putting this together. Cameron, Jen, Brian, thank you for your great presentations, and thanks to all of you for staying in there. All right.
Thanks, Julie.
Have
Nora.
a great rest of your day.